So today we'll be exploring the interesting topic of equations of straight lines and linear graphs. We will examine rate of change, gradient, slope. We'll be plotting lines. We will also learn the general format for equations of straight lines and how to interpret it. But how can we forget? We will certainly explore how linear graphs can be used to model real-world situations. But first, let's test.
How much they know.
How much do they know? Do you know the difference between an expression and an equation? Well, here is a list. Be sure to put them under the right heading. Let's start with the first one. 5x plus y. Tamika, is that an expression or an equation? Let's see. What do you know? It's an expression. How about 2x plus y equal 5? Let's see where that one will fall. Equations. Let's do two more and see if we can find a pattern.
Most definitely.
9 minus 3y squared. I hope our students are getting these correct, you know. That's an expression. How about 3x minus 2y equal 12? Expression? Equation? What do you know? It's an equation. You know, Tamika, I'm seeing a pattern here, you know.
I think they've seen it. So let's just see if they got it all correct.
Alrighty. X squared plus 3 equal y, equations. Xy plus 6, that's an expression. Xy equals 6, now that's an equation. And y equal x cubed plus 1, definitely an equation. You know, Tamika, I'm looking at this and I'm remembering what we learned in English class.
What did you learn?
Well, maths class still, but...
Well, you know, English for me wasn't so.
Well, you know, we learned about phrases and sentences. And now that I think of expressions and equations, I think an expression is a phrase.
Look at that.
5x plus y. What about it?
I have no.
Imagine us saying Tom and John. What about them? What are they doing? But let's take a look at the equations. 2x plus y equal 5. That sounds like a complete sentence. John and Tom are walking.
So let's look at the difference with an expression and an equation. Let us go to the board for a little. So we have 5x. I'm not sure if this marker is going to work for you. So let's try a different one. So we have, can you get that for me, please? 5x plus y. As my colleague said, Karima said that this is similar to a phrase in the English language. So what is the difference with a phrase and a sentence? A phrase gives what?
It doesn't express a complete thought.
While a sentence
expresses a complete thought.
All right then. So let's look.
There we go.
So these are numbers and variables. These are unknown. So let's say if I went to the canteen and I bought 5 patties for X dollars. That's my 5X. I bought 1 orange juice for Y dollars. I really didn't tell you how much I spent, you know, or if it was, I didn't tell you anything else. So this, I bought 5 patties for X dollars.
That's right. And an orange juice.
And an orange juice.
For Y dollars.
Actually, I'm going to tell you how much I paid for the orange juice.
Okay.
I paid $70 for the orange juice, and in total, I spent $450. Right? Now, I've given you a complete sentence, a complete statement, right? Now, I can use this equation and determine how much my patty cost, or you can determine how much I paid for a patty. So this now is a complete sentence, or what we call an equation in math. And this here is an expression.
You know,
it
Tamika,
is not complete. What would you change?
We want to also bring out the equal sign.
There you go.
Equation coming from the word equal. And as I look at this, I'm noting that there are terms on my, there are terms, or is a term.
Okay, and this is a term.
And so is.
All right.
And so is 70.
And this is a term.
Beautiful. So we have terms on the left-hand side and the terms on the right-hand side.
And we have, you mentioned?
The equal sign, of course. So students, of great importance, we must recognize that our equations must carry an equal sign and information must be on the left-hand side and, of course, the right-hand side. Now, let's explore a little bit more. Now we're looking again at 5x plus y. Tamika, you would have mentioned terms earlier. So students, can you tell how many terms are in this expression? You should be able to. So let's erase our equation and we're focusing now on our expression for a little bit, just so we can look at the terms. How many terms are in this expression? I'm seeing 2. Are you?
I know they got this.
They've got this, man. They've got this.
Because we would have stated that this entire thing with the 5 and the x is a term, and your y is also a term. So we have 2 terms.
Now here's a question for you. What is the coefficient of the first term?
What do you mean coefficient, miss?
That's a very big word. Now the coefficient is that number that multiplies our variable. Oops, there goes another word.
Variables.
Do we know what a coefficient is, what a variable is? Tamika, help our students to identify these.
So we're here again. So we're at 5x plus y. Now, as Karima said, a coefficient is that number that is used to multiply the variable. Now, I'm going to give you a clue. X and y, this eraser just won't stop falling. The variables here are x and y. What number is being multiplied? What number is multiplying the x? Coefficient is your 5. What about the y? What's the coefficient for y?
I don't see any number there.
Well, you can't see it. But how many y do we have on the board?
We have 1 y.
So really and truly?
But we also had 1 x.
No, we don't. Well, you have a point. But the 5 there tells us how many x we have.
Oh, so it's 5x.
So it's understood in the world of math that when there's nothing written there, it's a 1. So we have, the coefficient for y is 1, while the coefficient for x is 5. So your variables are your x and y, while your coefficients in this instance is your 5 and your 1. Did I get that?
That's right. But you know, Tamika, you know I love to refer to English, right?
Go ahead.
So we're talking about variables.
Okay.
Why is it called a variable? Sounds like any other word that we know.
Varied.
Values of x and y can change.
Look at that.
Look at that. And that's why it's called a
variable.
Beautiful.
So we're not yet sure what these values are. So they're variables.
I'm about to tell you now, though. Hear this. Now, what if you know that x is equal to 2? And y has a value of 3?
So what you're telling me is that x is equal to 2.
And y...
What is this again, everyone? This is an equation. And y is equal to?
3.
What do I do with that?
What would be the value?
Where my x is.
Okay.
So I'm substituting.
Okay.
Okay.
Sounds good.
So wherever I see x in my expression, I'm going to put my 2. And wherever I see, I'm going to just put back the coefficient just for ease. And wherever I see my y, I'm substituting
3
for 3.
Beautiful.
What do I do here?
Well, let's pause and allow our students to work that out. I'm sure they've got this. They have got this. Did you get that answer?
Yes, you did. I know. I see it on your face.
I'm so excited. We have brilliant students.
Oh, yes, we do.
Oh, my goodness.
So, what's next?
Let's check. Now, we said earlier that equations can be used to model real world situations.
Yeah, we went to the canteen a while ago.
Oh, we did, right?
Yeah.
Right.
We
So
got
now we graduate from school
Okay.
and we're launching a new electricity company.
Look at that.
Well, our students are. So you're launching a new electricity company. You decide to charge a standard monthly fee of $600 and $200 per kilowatt hours used. You are required to pitch this idea to your colleagues in a presentation or report. What should this report entail? Let's see. In your presentation, you must use a table to show how the total electricity bill changes as the kilowatt hours used increases. Number 2, you must demonstrate which type of graph can be used to model this situation. And 3, you must include an equation that will be used to determine the total electricity bill for any number of kilowatts used. Sounds like a big task, Tamika.
I think it's a lot of things, but I know
we can break this down.
I know these students got this.
So let's start with our table.
All right.
So here's our table on screen.
So first thing, let's just review for those who probably came in a little bit
All
later
right.
what we're doing. So you are now they're opening this company. They're entrepreneurs.
That's right.
Right. So you're now opening an electricity company. You are now going to be the person to pitch. A matter of fact, you're going for a loan because you really don't have all this money to start the business. So you are going to pitch some persons on what you think will happen with this company when you open it. You need to present a table showing how the electricity bill changes as the kilowatt hour used is increased. And we're going to start there. I'll fill you in as we go along. So,
but my first question, if I don't use any electricity, so the number of kilowatt hours is 0.
So Karima, you're really going to be home and use no electricity?
I shouldn't pay any bill, that's the point.
Yeah, but they're
I
going to charge
don't use any electricity.
They're going to charge you for something. Come on, man.
Boy, these people, oh Lord.
So that would be your?
$600? How?
Because sorry. The electric company,
the one that our students
yes,
are starting.
Opening,
okay.
They have placed lines in your house. Them don't invest just in case.
Used 0 and our total bill 600. Remember, we're working from the scenario earlier. How did we get that 600? So there were no additions. Now, how about 1 kilowatt hour?
Okay.
Let's look back at our table. So this looks like I'm paying my flat rate of $600, and since I only used 1 kilowatt hour, I am adding $200. That's what they said, right, Tom?
That's what they said.
$200 per
I'm
kilowatt
making
hour.
sure to write it so
Beautiful.
you don't forget.
Beautiful, thank you. So that gives us $800. All right, students, I'm sure by now you're seeing what's happening, so you should be able to fill in the table. So I'm giving you a few seconds just to do that. Did you get this response? 1,000. How was that calculated? Did you get 600 plus 200 plus another 200? Looks like 1,000 to me. Number of kilowatt hours used, 3. $1,200. How'd they get that? $600 plus $200 plus $200.
So from 4.
$1,400. $1,400. I didn't even bother to show you this calculation because I'm sure you've got this.
So now, Karima, they might be saying this is easy. They can just keep on adding 200, you know.
But it is.
What happened when you're really using electricity now, though? When you have lots of kilowatt, we're just going to add 200.
Sounds to me like we need either a graph or an equation. But they did tell us, Tamika, that we need that in our report.
That is true.
Students, you need that in your report.
Well,
Now, let's see. How would this look if we were to plot it on the Cartesian plane?
what is a Cartesian plane again, Karima?
All right, so remember on our Cartesian, our vertical axis.
Okay.
Now, we don't just go and put anything on any axis. We have to know what is independent and what is dependent.
So remember, students, when we have information, when you collect information, when you have any form of data, there are many ways you can represent this data. And we can do it either in a table or, as Karima will clearly explain in the next slide, a
graph.
There you go.
That's right. Now, before I even bring up the graph, because I don't want our students to just look on screen and see the answer, we have to get them to think a little bit.
All right,
so first
then.
we need to identify which is the independent variable and which is the dependent variable. So students, can you identify the dependent variable and the independent variable?
So remember, Karima just told you about the Cartesian plane. I'm just giving you, just to remind you of what it may look like. You said there's a vertical and a horizontal.
Right.
Okay.
Horizontal is called x.
Okay, so we have our x values here, and on your vertical we have our y values. Then you
Beautiful.
mentioned some other terms, independent and dependent variables.
Right.
So
first of all, let's figure out which is dependent on which in this situation.
Good.
So, from what I'm seeing here, my bill is calculated based on how many
much?
kilowatt hours I use.
Pretty much.
Yes. And so my bill is dependent on the number of
the
kilowatt
usage.
hours used.
There you go.
That sounds to me like my bill is dependent and the number of kilowatt hours is independent.
Independent.
Now we need to know which axis takes dependent variable
And which one takes the independent variable.
That's right. Now the x-axis is our independent variable. So let's see, we can zoom on our screen now.
Most definitely.
And we can see here that our x-axis has number of kilowatt hours used, and our y-axis, which is our dependent variable, shows our electricity bill. Now, Tamika, I want to pause right here and talk a little bit about scaling, because sometimes our students struggle so much with, identifying scales, etc. And looking at this, we're seeing that the axes, they are not moving by the same amount each time. They're not increasing by the same number each time.
Right.
Right?
So, as you can see on your y-axis, you are increasing by what that looks like 200.
200 each time.
Right.
But we also have to consider the spacing. So if we're looking at our spacing, we will see, am I allowed to?
Yeah, ma'am.
Can you? Okay. So we can see here that there is a space from between 0 and 200. There is a space of 1 centimeter.
1 unit, 1 centimeter.
All
sure.
right. So we're saying on our y-axis, 1 centimeter is representing $200. So if I was to move up another centimeter, I'm going to see an increase of 200. And if I was to move up another centimeter,
it would give you another
it would be another 200. All right. And if we look at our x-axis, we're seeing the 1 centimeter spacing, but are we increasing by 200 here?
That don't look like 200.
Doesn't look like it to me either. So we have the spacing of 1 centimeter, but our numbers are increasing by 1 each time. So our scale there looks like 1 centimeter representing 1 kilowatt hour.
Right.
And on our y-axis, we have 1 centimeter representing $200.
Now it's important because, as Karima said, sometimes you have, as you draw your graph, you're moving from the same 1 centimeter, you have 200, and for some reason, you just go up here and you skip out this one and you put the 400 here. So it's important to pay attention to how you use your axis and ensure that each unit represents the same what? The same value as you move, the same increment?
Increment,
Okay.
that's a good word.
Right.
All right. So
We didn't pay attention to the negative and positive. We're going to tell them
we will talk a little bit more about that shortly.
All right.
But let's see how this particular situation would look on the Cartesian plane.
Most definitely.
So we're looking at plotting. So I want us to zoom in on our screen here. So we did say from our table that if no kilowatt hour is used, we would pay
$600.
$600.
Oh, yes.
That's
because
right. I didn't want to pay
the
any, but
electricity company will charge you.
yes, my students' electricity company. So here is our $600. All right. What did we say? For 1 kilowatt hour, we would have paid $800. So we should see that popping in now. Beautiful. 3 kilowatt hours, $1,000. 4 kilowatt hours, $1,200 or $1,200. I'm seeing a pattern here, Tamika. Are you seeing it?
Yes.
4 kilowatt hours, 1,400. That looks like a straight line to me.
It looks like a straight line. I wonder if it is.
Wow,
look
what
at
do
that.
you know? It is a straight line. Now, I want you students to think and to tell us, how is it? Why is it that why do you think that this particular situation resulted in a straight line? Why?
We will have to explore this.
Yes, we should. And you know, to explore this, we can even look at our values for why.
Sure.
How are they increasing each time? So we started at 600.
We went to 800.
We went to 800. How much was that added on?
200.
And then we moved from 800 to,
1,000.
which is,
200 added to the 800.
and then we moved to 1,200.
That's 200 added to the 1,000.
Sounds to me like each time,
We're adding 200.
you know, Tamika, that is why we're getting a straight line. Yes, we have the same number being added on each time.
So for every kilowatt hour that is used, I will be charged $200 more.
That is right. That is so right. Now I want our students to zoom in.
To this graphical representation.
Yes, to this graph a little bit keener. We want to see how is this line sloping.
What do you mean sloping?
Well, you know, in layman terms, we talk about a slope looking something like a hill. So we may be going up a hill or we're going down a hill.
Okay.
So let's see which one this is. And of course, we are moving from left to right. So how is this line sloping?
Well, if we were driving, look like we'll be going up that hill. You know that highway, if you've ever driven on the highway, you see several of these signs showing you slopes. And this pretty much looks like one of those signs on the highway, except that it don't have no graph. You know, it don't have none of that graph thing.
So it looks like we're sloping upward.
We're going upward.
Yeah,
we're going up that hill.
That's right. So we are sloping upward, but why aren't we sloping downwards? Why are we sloping upwards? Let's see. What was that mean to our Y values again? Were they increasing or decreasing?
They were increasing. We keep on having more money to pay that electric company.
That's right.
We started with the 600, then they collected 800, and they just keep on going up. We're going to have to stop use light.
Oh, Lord. What will we do? Well, guess what? Interesting that you should say that, though, you know, because imagine we have a next scenario, yes, that speaks to some customers who use both solar panels.
Look at that.
And electricity generated by the company.
These people are smart.
Yes, they are. Now, suppose your company is willing to pay persons the same $200 for each kilowatt of excess electricity that they produce.
They sound like some money-making stuff.
If a customer produces more electricity than they need and sells 1 kilowatt hour to the company. So imagine, I'm the customer.
Right.
Sometimes I use electricity from the company,
Sometimes.
but I also have solar panels. So depending on the sunshine, there are going to be some months that I produce more than what I need.
Okay.
So we have a deal with the company, yes? Whenever I produce more than what I need, you pretty much pay me for that.
Sounds like a good thing.
Sounds like a good thing. So let's say that in 1 month, as this question says.
So hold on, before we continue. So what you're saying, say for instance, and we're using very small numbers here for kilowatt.
That's right.
Say for instance, you produce 7 kilowatts of energy this month.
Yes.
But you only use 4. What happens?
The company, according to this situation, will have to pay me for the 3, the excess 3.
Oh.
Sounds like a plan, don't it?
Okay.
Let's see how that would look on the graph, because we
All
need to
right.
find out what would this customer's bill look like. So let's zoom in, and here's our graph again. All right, so here's our customer's bill right there where that dot is. Zoom in a little bit more for me. And we're seeing here that it's mapping to a -1 because this customer
Have
sold
1
the company
kilowatt that
1
they don't
kilowatt
need.
that they don't need. So it's a
Okay.
-1 for them, yes? And so that customer would pay, what's that, Tamika?
$400.
$400.
Look like you can maybe not pay no money, you know.
Oh Lord, let's see. Now the point we're making now, if you notice, there is an arrowhead on this part.
But before you go to that arrowhead, Karima, that means if I were to make an excess of 3 kilowatts, I would pay no money.
I know you would say that, you know.
No, man, we have to. So you mean that this electric company can't owe me some money?
That's right.
Okay then. So, as you see, the graph shows you that if you were, hypothetically,
Yes.
produce excess energy and this company purchase this from you, pretty much you'd already have $600 for them. So they would deduct it until the $600 is completely finished, and then they'd owe you some money.
Sounds like a plan.
You were saying something about that arrowhead, though.
Right. Thank you. So we were talking about the arrowhead, and we're saying that what we're seeing here is just a piece of the line. And we know a line is continuous, right?
Most definitely.
And so the arrowheads are there showing us that this line can be extended in either directions. All right. So
What it means, you can basically increase the number of kilowatt hours used, or you can increase the number of kilowatt hours produced, that is extra, to sell to this electricity company. So this line can be in an infinite both ends. So you can either use too much or produce a lot.
that's right. Now, you know what's interesting though? We have answered 2 parts of the task. So let's
Look
see
at
if
that.
we have done our table.
Done the table.
Yes, and we'll see that table again shortly. And they did ask us to determine what type of graph could be used to model this situation.
So do you guys know what type of graph this is?
Well, it looks like a straight line graph to me.
I hope you said it was a straight line graph.
Linear graph it is.
It is a linear graph. So this here, and I mean, it speaks for itself. It is a straight line graph, commonly called linear graph. Welcome back to School's Not Out. You can catch this on YouTube as well as onestopmedia.com. If you're just joining us, we're exploring equations of straight lines and linear graphs. Remember, if you have any questions on what we've done so far, you can comment on YouTube and share them on Facebook.
Let's recap.
Most definitely. Remember, we're looking at expressions and equations,
Yes.
right? So now, I when we were thinking about it, maybe I didn't say some of the things that I should have, so I just
That's
want you
right.
to fully understand what we're talking about. So an equation here is what we call a true statement.
Right.
1, it's a true statement. And next, I don't want you to forget this, an equation. Karima had highlighted that you have this equal sign. It's very important to this term. So they are equated to each other. Did I get that?
That's correct. And remember, we can have more than one terms on
Most
the right-hand
definitely.
side as well. So the important thing is whatever is on the left-hand side is equal
to the value.
what is on the
Right.
right-hand side. Everything that's on the
So I
right-hand
could
side.
have written this as 10 plus 2. because it's still 12.
All right, so we could have done that, or could have variables too, but we'll explore that in another lesson.
So remember, equations are true statements, and they must be equated to both. Left side must be equated to the right side. You just joined us. So we were looking at if you were an entrepreneur, you just opened an electricity company, you were asked to pitch this to your, what you call those people who finance you? Your come on, Karima. They finance you, the bank. Those persons, your
financial institutions and investors.
Good. So you're pitching your meeting and you want them to know how it looks, how it will look if you remember, if you did more than enough or you did too little. And this is where we were. You were asked to do a graph and also to represent the information in a table. Right, we did the table. You want to look at the table 1 minute?
It's going to come back up because we're going to need to use it now to find out the equation of that line that we just saw.
Awesome.
So I want to point out here, Tamika, if you look at the calculations carefully, and I've highlighted it in red, and I hope our students are taking note, that this 600, it appears
all the time.
All the time. It never changes, and it appears the same number of times each time.
One time.
One time. So there's a word that we use when something is not changing. What is it again?
Shall we see?
Yes.
Anybody know that word?
Constant?
That's right.
Thank you. All right, so we can say then, this is exciting.
Yes,
we can
600
say then that the 600
is our
constant. No, but let's take a look at the 200.
For this particular scenario.
Yes.
Every time you just keep on adding that 600.
It is there.
It is
in
there.
Each calculation.
It is there.
All right. Now, let us look at the 200 now, Tam.
It's not there in the first one, though.
All right, so it's not there in the first one.
No.
But we're seeing how many times did it appear in the second. So I want us to zoom in on the screen a little bit more and see how many times do we have 200 here?
Once.
How many times do we have it here?
Twice.
And how many times are we adding it here?
Thrice. 3 times.
All right. Can you see any connection between the number of times we're adding it and the number of kilowatt hours used?
Most definitely.
Tell me what you see.
Okay, for the 0, I've used nothing. I've been home, I plug out everything. A matter of fact, I got turned off the main switch in my breaker. 0 kilowatt use.
All right.
0 money added.
That's right.
All right, so I wanted to warm some tea and I used 1 kilowatt.
All right, and we see that 200 appearing once. And for 2 kilowatts,
I'm bored.
Appearing
I turn on the TV.
twice.
That's right.
But you know,
3
times.
3 times.
Could we have written this using multiplication? Isn't multiplication repeated addition?
It is.
It is.
It is.
So hold on. This 200 that is written 3 times. 200 plus 200 plus 200. Could we say 200 times 3?
Most definitely, it would still be 600.
Beautiful. And you know what else I noticed, Tam? The number of kilowatt hours used keeps changing.
Yeah.
Sounds similar like we need a variable for that. Didn't we say variables change in value?
We did say the variables change.
And based on where we had it on our graph, we can refer to the kilowatt hours as X because we had it on the X axis.
Most definitely.
Yes, and we can refer to the electricity bill as our Y.
And as you rightly said a while ago, your X and your Y's are variables that change. If you look on your Y and X axis, what's happening to the numbers? As you move to your left or your right.
All right, so as I move right, I see them increasing.
So they're changing.
Changing,
and those are your X values.
That's right.
As you go up vertically, I should say, you are increasing, and it's changing.
All right.
So it stands.
So let's look back at this table because we want to get this equation thing right.
Right.
So my 600 is always there. Please write it on the
board.
board.
All right. So I'm always having to put this $600.
Yes. And I'm always adding it to...
What am I adding it to? To 200.
200, but the 200 is being multiplied.
Right.
By... what do you know? The number of kilowatt hours used. What did we say we're using to represent that again?
We said X.
X.
Because it's on there.
Right.
So we're going to put it here because we don't know how many kilowatt hours we might use.
So they asked us for an equation. Is that an equation, Tam?
You know,
That
is this
looks
an
like
equation? This, what is missing from this? Why is this not an equation?
You're forgetting the equal sign. So what is it that's equal to? What is it that we're working out? The total bill.
So,
Y? Can we call it Y?
We can.
Yeah, we can, because we're talking about the graph.
So let's
call
not
it
write
Y.
total bill.
Let's call it Y, because that's
So
what it looks
Y.
like.
So Y represents our total bill.
Sounds to me like we have answered all the questions. I hope that our students have done the same. So the equation for this line, guys, it's Y equal 200x, plus 600. This is interesting stuff.
You see, I have 600 plus 200x.
Equal Y.
Now,
Does it mean
positive.
the same thing?
So I can rewrite this. I can decide to put 200x first, and then I add the 600 to it, and I still will equal my
All
Y.
right.
And I can also do it the other way too. I can say Y equals 200x. I have not changed the value of anything, have I? I've rewritten it, but they still stand.
Now, I want us to delve a little bit more
into this Y equal 200x
yes, because I want to know if
600.
this equation, if somebody uses 10 kilowatt hours, because I'm not seeing 10 kilowatt hours on my screen, can I use this equation to figure out that person's bill?
All right, so remember that you had said to me that the X represents the number of kilowatt hours.
For this question, right.
So what you said now, if 10
if the
kilowatt
person uses
is used.
10, yes.
So remember when you were telling me, what if I knew the value of the X and Y from the previous thing?
Right.
And I had substituted that the value of X.
Right.
So what you're saying now, this is a number of kilowatt use, and you just said 10.
10.
So I'm going to substitute this X
with 10.
Let's see what happens. I'm going to take
As a matter of fact, let me save you some trouble.
Okay, look at that.
And guess what? I know our students are lightning fast.
Let's give you some time.
I am thinking that they
figured it out already?
They are brilliant.
All right.
They're brilliant. And 10 is a pretty easy number to use. So there's your substitution. Where X is, we have our 10. 200 times 10.
So for every 10 kilowatt, how much will you be charged? $2,000. Or remember, they have some wire in your house, so you have to remember that you have to pay for those wires.
$600. Total bill, $2,600. You know, Tam, in mathematics, we always say we don't take one situation and make a rule, not true?
Right, let's see if it works again.
We're gonna see if it works again. But before we do that though, I want us to realize this 200, because we're learning now. I'm gonna share this with you. It's so interesting that the equation of a straight line can be written as Y equal mx plus c. Clean up that board for me, Tam. And let's write down that Y equal mx plus c, because we need to figure out what is m, what does it do, what is c, what does it do. We have to do that before we end this session. So write that for me. Y equal mx.
Y equals m. X.
And as she's writing that,
again, plus C?
As she's writing that on the board, we need to remember that m is a real number, and c is also a real number.
Okay.
Now, as we look at the equation we just had, y equal 200x plus 600, we can see clearly that the 600 would be our...
What if I can't see it, miss?
Oh, you can't see it?
No.
Oh, didn't we say 600 was a constant?
So let me just write that equation below this for you.
Okay. Sounds like a plan. All right, fine.
Okay.
Beautiful.
So C is?
600.
C can be equated to 600 in this instance.
In this instance,
and
thank you.
M can be equated to 200.
You know,
or the value of M is 200 in this instance.
That 200 sounds like the 200 that keep adding on each time. Wasn't that where we got it from?
Yes, we did.
So you know we can call that the rate of change.
Most definitely.
The rate
Every time you move
change.
up on that graph, you are adding this 200.
But like we said, we need another example because we don't want to run ahead of ourselves.
Let's
check this one out. So y is equal to negative 3x.
Go ahead.
It's maths, you know, use lots of space.
Yes, I'm going to just put that here. So y equal negative 3x.
Plus 1.
Plus 1.
So,
you can see it on the
based on what we just learned, we're saying that 1 is the constant, and we're going to learn a little bit more about that one in a few. And our rate of change is -3.
Right.
Tom, what do you think that -3 mean?
You know,
We're increasing
we had
by
200.
3. Are we decreasing by 3?
Can you increase by -3?
But technically, that would be a decrease,
Right.
wouldn't it? So we're decreasing by 3.
Decreasing by 3.
All right. So here, what you're going to do for me, we're going to check the first 3 of these and see if that's really what is happening.
So what you're saying, if I knew the value
of
x,
yes,
and I were to substitute it into this equation, I could then figure out what the value of y is.
Excellent.
Okay.
I hope my students are on point like you are.
All right.
All right. So you're going to just do the first one so that
Yes.
our students can see.
Most
and
definitely.
then
So the first
they
value
will-
that I'm using for x is -2. And remember, this expression equals this expression. Or this term is equated to these terms.
Good.
So, -3 multiplied by -2.
+6.
All
That's right.
So when a negative meets anything, it changes its sign. So negative, so this is 6. We don't write positive, so we just put 6. And then we have what we do with
Plus
the 1.
1.
Plus 1. Y is equal to 6 plus 1. What is that? Come on, that's easy.
Yep.
So that's 7. So
Beautiful.
now we're going to look at
All right.
how we put this on the graph. How do we represent this graphically?
So let's put those up.
Or coordinates come in this format. We have an
Beautiful.
x
And a
a y. So your x value here, what did we substitute for the
-2.
right?
Was that it?
So we substituted -2 for the y, and we calculated that the y value is now
-2 for the x. Did you just
for
say
the
y?
x. I am sorry for
That's
the
right.
x -2,
Right.
and for the y we got
7.
7. So one of our points on this particular line, this is an equation of a line, 1 point on it can now be plotted using -2 for your x value and 7 for your y value.
All right. So our students, I know they're on the ball and they know how to do substitution because we did check that earlier.
Yeah, we did.
So we want to see how does this graph look. But you need to tell me, Tam, if we're decreasing by -3 each time. We need to check that, by the way.
Before we even look at the graph, let's
yeah,
look.
let's look. 7, then 4. That looks like a decrease of 3. 4 to 1. Looks like a decrease of 3. 1 to -2.
So let's just, for those who may not fully understand this, let us just look at that one little bit. So how we move from that 1 to -2, Karima?
Use that number. Ah, girl,
So
you're
let's
thinking what I'm thinking.
Let's
Beautiful.
just help those who may not fully understand how we get that -2.
And how we see that difference of 3 coming out.
So because
there.
I'm heading to -2, I don't even need any more. So where am I again?
You're at 1.
I am at 1. So I'm
So
here,
we're looking at 1 here,
right?
and we're seeing.
And I am decreasing by 3.
yes.
So I am going 1. When I decrease by 1, I end up, so you had $1 and you decrease by 1, you end up with $0. So if I decrease by another 1, now you owe somebody $1. So you're at -1. And 3, so this is 1, 2, 3. I now end up at -2.
So we are seeing that -3 is actually again the rate of change.
Right here.
So we want to see how does that look on a graph.
This graph looks a little bit different though.
Yes. If I'm driving, this looks like I'm going downhill this
Well,
time.
if you're driving from left to right, sure.
If we're driving from left to right. But that's what we are going to be
Yes,
looking at.
we're
So every
always
time we're
moving
checking a
from
graph, left
to
right.
right.
Right. Beautiful.
So we're coming from Mabay now. We went to Mabay a while ago and we're coming back home.
All right, so we can see here that the -3 is resulting in a downward slope.
Most definitely.
Look like we can make a conclusion now. So a positive rate of change, give me
with the positive 200 that we had,
give me an upward slope. And a negative rate of change gives me a downward slope. And you
From
know,
left
Tam,
to right. Remember.
I want our students to understand as well that rate of change is the same thing we call gradient.
So let's put that
It's
word
the
on the
same
board
thing
for
we
them.
call slope.
Aye.
So we have to ensure that they understand that. So we refer to it as the rate of change.
Oh, I took off your... Okay. So we said that This value M represented rate of
Rate
change.
of change, also known as gradient or slope.
Gradient or
Slope.
slope. All right.
Now I want to zoom in on the C value now, Tam.
Yes.
So I'm looking at this graph and I'm looking to see where it meets the y-axis. Woo! What's that value there?
Looks like 1 to me.
Positive 1? Negative 1?
It looks like positive 1.
Positive 1.
Positive 1.
Let's check our equation if we could get that information anywhere there. Oh, what do you know? Here's a
right
plus
there.
1, it's right there.
It's right there.
And so we can say that our C value, while it is a constant, it also tells us where the graph must meet or cut or intercept, whichever word you want to use, the y-axis.
So when you look
Beautiful.
at the equation of a straight line, you see y equal mx plus c. We have determined that, or m tells us the rate of change, and it also indicates whether it's positive or negative, indicates which direction the slope will go.
Right, from
All
left to right.
Do you remember which direction? If it's a negative, where does it slope? Did you say
Downward.
downward? Correct.
That's right.
And if it's a positive, upward. So
Excellent
you're
stuff.
doing well. So we use the term gradient or slope commonly in class, and you must remember that it does represent the rate of change. Then we now know that
The C.
the C, which in this equation is 1,
Yes.
is also some valuable information. It tells us where
The graph meets the y-axis.
or intercepts with the
intercepts.
y-axis.
Good. No,
Or-
you know, Tam, I see we're coming up to a break and I really want to get this in so that when we come back from the break, we can actually, do our wrap up.
Most definitely.
So, can you state the equation of this line? What do we need? Gradient?
Yeah, we need the gradient, and we need
And
to know where it intercepts the y-axis. I can tell you that already.
Where?
0.
0.
0.
0. That's right. Let's look at the gradient. Ah, we see a movement there. Are you seeing
Okay,
it?
so remember we're moving from left to right.
Yes.
So I have moved 1
1.
to the left,
Right, and let's see where I move now.
2
Where? Up or down?
down.
So that's a...
negative movement.
Whew. So what's my gradient here?
Oh, let's see. So
What's the rate of change?
y would be equal to, is that 1?
Change in y, right?
Uh-huh.
So the change in y, no.
So
change in y is negative 2,
I was gonna,
and the
okay.
change in x is 1. So this is your gradient.
Uh-huh. Oh, so you're not writing it straight? Okay.
So remember, we
Okay.
can get this from our graph.
All right, fair enough.
So we're looking
And C?
at the change that is taking place, and C is 0.
Okay.
Which bright student can tell us the equation of that line?
Our lesson today is all about exploring equations of straight lines and linear graphs. We're going to ask you a question to see if you were listening, and we'll see who answered correctly at the end of this section.
So here's the question. What 2 components are necessary in writing the equation of a straight line? We'll give you the answer at the end of our show.
If you missed the question, here it goes again. Karima?
What 2 components are important in writing the equation of a straight line? Again, we answer at the end of the show.
Awesome.
All right, now Tamika.
Yes. Oh, we're going to look up a little bit
We
at what
wanna
we're doing.
we wanna remind our viewers that whenever we are working or calculating the value for y, as we're getting our ordered pairs, that we're substituting a particular value for x. So in this case, we substituted negative 2, and our rate of change was negative 3. So a negative 3 times a negative 2
Gives
actually
us a
results in a positive 6.
6.
And remember our constant or our y-intercept.
Right.
That needs to be here. I must also remind or say to our students that we have worked so many positive y-intercepts,
Yes.
just so you know that our y-intercept can be negative. All right? So 6 plus 1 gives us 7. And so we have our ordered pair, -2, 7. And then we could plot on our graph paper.
And
now,
okay.
Imagine you are a contractor at your school, Tam, and you know, we're making our schools wheelchair friendly.
Most definitely.
Right. So
we'll have to.
You're required to build a ramp. We have 2 options.
Ramp
Let's
1.
zoom in on the screen, yeah? Ramp 1 and ramp,
Ramp
2.
2.
Which ramp has the higher gradient? Which gradient is greater?
Well, what did you say? Did you say ramp 2?
That would be correct.
That's right.
You know what's interesting? Because I'm looking at this ramp and I'm seeing where both ramps, they are covering the same vertical distance.
Yeah, the height looks pretty much.
And on a graph that would represent the change in y.
You would run that along your y-axis.
Beautiful.
You see that?
But
Awesome.
now I'm looking at ramp 1 and I'm looking at the horizontal distance, and it's a very large distance,
yes.
long distance rather. And as I look at ramp 2, it's a shorter distance.
Right.
So I'm seeing here that because we're covering the same height in a shorter distance, we end up with
Clearly have to go at a
steeper slope.
Yes.
That's right. So
That
which
same
of these
highway
ramps,
again.
Which of these ramps would you put in your school, Tam?
I think I'd go with 1.
Yeah, because
Yeah.
you don't want to be pushing
Because
a wheelchair
Up the
up a
steep.
steep slope.
They're going to fall.
I'd go with ramp 1 as well.
Yes.
I guess we are on point here. So, you know, before we close, we must engage our students
With a
in a
possible
CSEC
CSEC
question.
question.
That's right. So this question asks us, well, they gave us 3 equations.
Right.
And they also gave us 3 lines.
So you have a diagram and you have 3 equations.
And we're pretty much expected to match the equation to the line. All right. So let's look at line 1.
Now that you know about this equation of a straight line, looking at that graph, can you tell anything about that line, that graph?
Well, I can tell you one thing. Well,
Tell me.
I see 2 lines
Tell me, look at
intercepting.
line 1.
Hold on. Before
Oh.
I see 2 lines intercepting at the y-axis at 2. So
Okay.
if I'm choosing, I know it's gonna be either between y equal 2
Or
y equal x plus 2.
There you go.
Because I know that these 2 is telling me where the graph, the line
Intercepts
there is supposed to intercept
the
y-axis.
y-axis. Okay.
But I'm looking at y equal 2 though, Tam.
What is
That looks like a c value only.
Because
What happened to the gradient?
Yeah.
Where's m?
Where's the
Oh, you know what?
So maybe that line 1 wouldn't go with that one. Because we are seeing a slope. Okay.
So m being 0 means that we have a horizontal line.
So what
there
you're
is no
saying-
slope taking place. There is no incline. And so we have a horizontal line. I think we have line 3's equation.
So pretty much what you're saying, that line 3 is representing me walking across this floor.
This very flat level.
Leveled
floor.
I'm assuming that if I drop a level on it, it would balance out.
That's right.
Good. So y equal 2 would represent
Line 3.
3. Okay. We're still back at line 1, miss.
Yes, but Tam, you don't see the beauty about it.
No.
If I've already decided, remember that the y-intercept is 2.
Oh.
And I've already ruled out line 3 to be y equal 2.
So y equal x plus 2 clearly is line 1.
That's right. Isn't
Let's
that
look
smart?
at that. Yes, it is.
It
It
is.
is.
Now, let's look at y equal x.
Well, miss, is only 1 line leave.
Oh, yeah, right. But we still have to explain why.
Okay, please.
So, yes. So, looking at y equal x, can we say what the m value is?
Let's
Or the
see.
gradient? From the equation.
It's, you remember when I was explaining that if you see nothing in front of that variable, what is the coefficient?
Right, the coefficient is 1.
And if the coefficient of x also represents the gradient, then the gradient is
1.
1.
But I'm not seeing any c value, Tam.
Oh.
But we did a question where we said y equal
yes, we
negative
did.
2x because that line passed through the origin.
origin.
That's it. So let's see if this one passes through the origin.
Yes, it does.
Beautiful. So we have it. So let's recap. Line 1 is y equal x plus 2.
For those who, let's just run that
Line
here.
2.
Okay.
Line 2
You're
is y equal x.
That's
and line
right.
3, the horizontal line
is y equal
2. Beautiful. They asked us as well to show the gradient. Show that the gradient of line 2 is 1.
We kind of did already.
How did we say? Yeah, but we're going to show.
Okay.
We're going to show, so we need to, refer to the diagram, separate and apart from the equation.
Sure.
We're going to show. Yes, I'm going to step over to
So remember,
here.
you're moving from?
So we're looking at change in y, and we're looking also at change in x. So it's change in y divided by the change in x. So we're looking at line 2, and what's so beautiful about this diagram is that there is already a little triangle, a right-angled triangle in the diagram that I can use to my advantage.
Right.
So let's take this point on line 2 and let's see what our change in y is. I'm moving in a vertical way, and so I'm looking at change in y, and I'm moving up. So my change here is a change of positive 2. You can write that down, Tam.
Okay. So it's my y, change in y. Guys, remember, change in y. I don't remember that sign.
All right.
Over change in
x. So our change in y, we said here, is 2. And we're now going to be checking our change in x. So we're moving horizontally. So here we are at 0, and we would have moved to 1, followed by another move here to 2. So it looks to me like our change in x is also a positive movement of 2.
So our
gradient
is 1.
Was that what they asked us to show? Show that the gradient of line 2 is 1. Excellent. We've done it, guys. We have done it. So we're going to move from our screen now as we wrap this up by just sharing with our viewers the things that we learned from today's lesson. So we learned today that any real world situation that has a constant rate of change, yes, can be represented using linear graphs. We also learned that the general form of an equation of a straight line is y equal mx plus c, where m represents the gradient and c represents the y-intercept. We also learned that gradient is also called rate of change or slope. We learned that positive gradient means upward slope, while negative gradient indicates a downward slope. We did promise our viewers that we would give them the answer to the question. What are the 2 components that are important for writing the equation of a straight line? What are they, Tam?
They are 1, the gradient, or
the m value, which is called gradient. What again? Rate of change. And slope.
That's right.
All right. So either gradient, rate of change, or slope. That's 1. And the second thing is our y-intercept. Thank you for tuning in, and congratulations to our viewers who text in the correct answer. Have a good day. To Tanya, did I get that name correctly?
Tanya is the person who texted the correct thing.
Beautiful.
Awesome job,
Tanya.
Tanya.
Awesome job. Be sure to tune in tomorrow.